So imagine you are given a simple task to increase the conductivity of a semiconductor at room temperature. The obvious solution would be to increase the doping levels, that is to increase the number of free carriers. But now on the other hand, if you are asked to increase the resistance of the semiconductor, that is, make it behave more like an insulator, then the first question that you might ask is, why not just use an insulator, or else why not just use an intrinsic semiconductor? So in this video, I'll be explaining why both the solutions is not applicable when we are targeting high frequency applications, and I'll introduce this new class of materials called semi-insulators, which is a very important material when we are actually trying to design high electron mobility transistors, which is commonly called as HEMT. Firstly, let's try to understand what's the problem at high frequencies. So let's look at the cross-section of a IC technology. So typically what we have is a substrate that is actually made of a semiconductor, and you have a epitaxial layer which is also a semiconductor. So you can think of this epitaxial layer as a better version of this substrate, which is more clean and where the doping levels are controlled. So this is where your transistors are made. So once you have your transistors, next you'll have metal layers. So this is metal 1, metal 2, and vias connecting them. So when we make circuits, usually the substrate is tied to ground and your signals are actually routed using the metals. So inherently we can see that there is a capacitance between your metals and the substrate. So basically whenever you have two conducting plates and you have an insulator between them, you form a capacitor. And here the insulator is nothing but your silicon dioxide. So between each metal layers and your substrate, you fill silicon dioxide. At low frequencies, these capacitors are not that big of a issue. But as the frequency increases, the capacitance will start behaving like a short. So what I mean is, we know that the impedance offered by a capacitor is given by 1 by j omega c. So as this omega increases, the impedance actually goes down. So at higher frequencies, the capacitor will start behaving like a short. So basically what happens is, now your signal will start leaking into the substrate. And because of this leakage, there will be substrate currents that will start flowing. And these currents are actually not desired because they just add up to the power consumption. So now our goal is, how do we reduce this current? So the first solution that we had is, why not replace the substrate with the insulator? So what I mean is, make the substrate an insulator and then grow the epitaxial layer, which is a semiconductor, on the insulator. Now let's see what is the problem when we are trying to do this. So the first thing we have to consider whenever we are growing two different layers is, the lattice between those two layers should match. So in simple terms, what this means is, the atomic distance between the atoms in your insulator should match with the atomic distance that is there in your epitaxial layer, that is your semiconductor. So basically it means that if you want your epitaxial layer to be crystalline, and the substrate you use to grow this epitaxial layer should also be crystalline. Now if this atomic spacing do not match, what happens is, when you start growing your epitaxial layer, so there will be stress that will start building up. So a simple analogy to understand what is happening is, so suppose you have a curved surface and you use tiles of very small height to actually fill this curved surface. So since the height of the tile is very small, the curvature is actually not noticeable. Now as we start increasing the height of the tile, we'll see that the curvature will become more noticeable. So this is what happens when you try to grow the epitaxial layer in a substrate where the lattice is not matching. So as you keep growing your epitaxial layer, the stress will keep building up. So as the stress keeps building up, your epitaxial layer at the top will start having cracks. And it's very important to note that the epitaxial layer should be of very high quality, because this is where you actually make your transistors. So any defect in your epitaxial layer will directly translate to degradation in the performance of your transistors. And the next important point we have to note when making such layers is, the thermal expansion between those two layers should also match. That is, as we increase the temperature, the amount at which the insulator expands should also match the expansion rate of the semiconductor. If that doesn't match, then again you will have some stress that is building up in the epitaxial layer. So of course we do have a technology called SOI, that is nothing but silicon on insulator. But the way it is made is different. It's not that you have an insulator and then you grow your silicon. So one of the way how it is done is, you have your substrate above which you grow an insulator. And in case of SOI, the substrate is silicon and the insulator is SiO2. And you make another wafer with a silicon substrate and above which you grow a epitaxial layer. And now what we do is, we take this second wafer, flip and place it on the first wafer. So that is, your epitaxial layer will actually be facing your insulator. So you'll join them by heating, that is, these two are joined. And once it's joined, it will be chopped. And this part is used to make the transistors. So this is one of the way of making silicon non-insulator, and it is very important to understand that this is only possible for silicon. So the reason why silicon is most widely used semiconductor, even though we have semiconductors with better properties, it is because of the fact that you can grow a high quality insulator on the silicon. So what I mean is, you have your silicon substrate and this is your insulator, that is SiO2. So when we mean the quality of SiO2 is very good, means that the interface between Si and SiO2 is very good. So why is this interface very important? So this is because at the interface we can see that one of the bond of the silicon is actually not satisfied. So that is, these bonds are not fulfilled, and this is what we actually call as dangling bonds. So this is also one of the important consideration that we have to have whenever we are making such interfaces. That is, the dangling bonds at the interface is very low, and in case of silicon and silicon dioxide, this interface bonds can be really low. So this is one of the reasons why silicon is most widely used, and of course it is used to even make silicon on insulator. So from this discussion we can see that directly replacing the substrate with insulator does not work. So we'll look at the next part, that is, why not just use an intrinsic semiconductor. So let's start by looking at the energy band diagrams. So we know that in case of an intrinsic semiconductor, the Fermi level actually lies in the middle of the band gap. But it is important to know that it is practically impossible to make a pure intrinsic semiconductor. So there is always some level of impurity that actually degrades the quality of semiconductor. So if you look at the energy band diagram, basically your Fermi level shifts either up or down based on the type of the impurity. And the next thing we have to note that is, even for an intrinsic semiconductor, the free carrier concentration at room temperature is not zero. That is, Ni is directly proportional to e power minus Eg by kT. And in case of silicon, we know that Ni at room temperature is approximately 10 power 10 per cubic centimeter. So this is not a small number. So even at room temperature, we have this many number of free carriers. So this just concludes that we can't use an intrinsic semiconductor, and also we can't use semiconductors with low band gaps, because as your band gap decreases, your intrinsic carrier concentration increases. So now the question is, how do we make this new type of material that is called semi-insulating materials? So the first thing we noted in an intrinsic semiconductor is the Fermi level actually shifts based on the level of impurity. So our goal is actually to pin the Fermi level at the center of the band gap. That is, we have to make sure that the Fermi level stays at the middle of the band gap. And the next thing is, we can't choose a material that has lower band gap, because lower band gap materials by default will have higher intrinsic carrier concentration. So usually when we are making semi-insulators, we don't choose silicon. We choose materials such as gallium arsenide, where the band gap is around 1.4 electron volt, or else gallium nitride, where the band gap is 3.4 electron volt. So the first choice is choose wider band gap material. Next, let's see what is the problem actually caused by these impurity levels. So basically what happens is, so if you have a dopant type impurities, then it will create energy level that is close to the conduction band, ED. And this donor levels can actually donate electron to the conduction band and increase the free carrier concentration. On the other hand, if your impurity is acceptor type, and then it will have energy levels that is close to the valence band, and this will accept electron and give rise to hole, which also increases the free carrier concentration. So now the goal is clear. We have to stop this donor levels and acceptor levels to contribute to the free carrier concentration. So what we do is we add deep impurity levels that is very close to the Fermi level, and the goal of this impurity levels is to actually capture the electrons from the donor sites or release electrons to the acceptor sites. So what I mean is, instead of the electron moving from the donor level to the conduction band, now the electron sees that it has a lower energy level to which it can move. So the electron will move from the donor energy level to the deep impurity level. And similarly, instead of the electron hopping from the valence band to the acceptor energy level, the deep impurity actually provides electron to these acceptors. So once these acceptor states are filled, now the electrons won't have any place to jump from valence band to the acceptor levels. So it is important that these deep impurity levels that we actually introduce in the semiconductor should behave both as acceptor level and donor level. And for this reason, usually transition metals are actually used to make these deep impurity levels. And one of the common example is gallium arsenide with chromium. And this technique of actually implanting these deep impurity levels is what is referred to as compensation. So this is how you actually make a semi-insulating material, and this material can now be used as a substrate to make transistors when we are actually targeting high frequency applications. And in the beginning we mentioned that to increase the conductivity of a semiconductor, we increase the doping levels, and it is also important to understand what cost we pay when we are actually increasing the doping levels. So you can refer to my video where I explain the effects of higher doping levels in a semiconductor. So that's it for this video. So have a nice day and thanks for watching.